So, okay, let's try to do the QFT now with this thing. Let me recap. So what I did here is circ interference superposed with an initial state as a seed, then an interference map. That's kind of what I'm not super convinced with, that this is the right way to think about it, but just for the moment, okay, just for the moment, okay, so this is just supposed to basically say, just rotate that state, kind of, yeah, and then superpose. And so what that superpose is going to do is like here inside, that this is kind of creating interference, right? And so because what would be cool is if these kind of, if you could debug that superpose function and say, sort of show interference is true, right, or something like this, and then kind of that would basically show you where the interference is happening, or that you could kind of step by step go through these, right, and then see kind of what's happening in here and see if that's really what you want to do. Maybe a visual interference map designer would help somehow. I don't know. For small scale, that's definitely interesting. But what happens with QFT? Is this something that feeds in there as well? That's my question for this video. Cool. So what we're gonna do is I'm just gonna do it here. So this is basically QFT, and so this is Grover. Just because this is, as I said, it's not really Grover. This is not really something that exists. It's just it's just me playing with ideas. Okay, so so what we do with the QFT? So with the QFT, we want to do let's start with the inverse QFT. Okay, so the input is it's a number, binary representation of a number, right? Say, for example, let's say of a natural number. Okay, just to make it simpler. So let's say, for example, 001, right? The output of this output is 001 in QFT basis, which is basically I like the way to see it as it kind of, if you take a look at the different phases of your equal superposition, it does one full cycle. So this means that, so this would mean something like, you would have you've got like your, maybe let's say with 2 qubits because it's going to be easier. So, right, and so you kind of have your values, right? So your keys. So 1 0 and 1 1, right? And so the phase in here should be the phase should be 0 degrees, right? The phase in here should be 180 degrees because we're done with a half, right? And so that should be 90 degrees, right? And that should be 270 degrees. 270 degrees, I think so. So this is 0 this is 0 1 in QFT basis, I'd say, if I'm not wrong. So this is, if you like more a visual representation of that, and you kind of have, so if you imagine, I'll just show it quickly, it's going to be easier sitting quirk, okay? So quirk. So we're going to do I think from to phase frequency, I think this is, I know it's okay, so it goes, yeah, maybe. Yeah, QFT. So it kind of does this. So this is 0 degrees, 90 degrees, 180 degrees, minus 90 degrees. Okay, but it's 270 degrees. basically. So this is what it does. Okay. How would we do this? So the way this works, right? The way the circuit works. Maybe I shouldn't think about the actual circuit because that's the whole point here, right? Now the question is, do we wanna get it to a superposition? I guess so. That's the first thing we want to do. So we want to kind of have the same thing. So we want to superpose our state with the same initial seed. Okay. So we're gonna do 2 qubits this time. And now what we're gonna do is we wanna somehow create because here we're not doing any interference really. So it's a bunch of superposing with. I'm not happy. It shouldn't be called interference map. It should be called phase map. Because it's not. You're not mapping the interference, right? There might not be interference. So maybe we should just call those things phase maps. Doesn't this become then just because superposition happens when no, I again, interference map doesn't necessarily mean there's going to be interference. It's just the way you want to map it. So I hope that was not hearable. Because then I'm not so sure that what you do first is a superpose. You have to definitely. So what would mean, for example, right? So what would mean? Okay, what if we would create an interference map? First thing we're going to do is an interference map where we say take that to 180 degrees. Okay, take that to 180 degrees. But it sucks because that basically is telling you that you know. Because here I know a priori, I know the solution. So I should do something that's solution agnostic, right? Because here I know what I'm doing. I know that it's 0, 1. But if I wouldn't know that, I basically would need to know. We need to go digit by digit and say, yeah, that's a bit unfair. The same happens here, right? That's not how you. But let's do it first this way. But you know what I mean, right? So I should usually, what I would usually expect here is I would kind of loop over these, and that would be really a loop actually. That it basically says, if the first digit is a 1, right? We know that the whole thing. Oh, look at this. Yeah, I like that. So look. So maybe it should be something like this is fake code, okay? Pseudocode for each I in okay, or in number, let's say P, okay? So P is our input. So P is I'm so bad coming up with a P equals whatever 0, 1. So for each of those things, right? So if I know that if so here's about parity. The way this QFT base is built is about parity. So if I equals 1, I know that I have to do something, right? So okay, but that should be maybe part of the interference map definition, right? So the interference map here should basically say that, for example, mm, mm-hmm, mm, something like that should be some kind of expression or regular expression, where it's like, not regular expression, but it's like, um, mm, 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 for all the, I want to say, what I want to do is something like this, right? So for these kind of elements, we want 180 degrees. If I is 1, right? Because if it's 0, we don't want that. So this is kind of how you would build that, I guess. How could you express that from a language perspective? Because well, then it's just kind of a mask, right? I mean, you wouldn't even need to do these like these. Because it's not always 180 degrees. Because what this does, right, is if I so that's why in the circuit, the way you do these, right, is how do you do it? So you do a swap, right? So you do a swap here, and then you do you apply a Hadamard first, or I think you apply a Hadamard first, and then you do a control. Z, then you do a Hadamard there, and then you apply a Z. No, an S. Yeah. So that will be. So that's the actual circuit. So I ended up thinking about the circuit, but that's kind of what from interference perspective, or using these concept of a language, you would say. You would kind of say, look, the reason. No, knowing the structure, right? So if you know the structure, so knowing the structure here of what's the QFT basis and how is it expressed? I would say, I'd say something like that. So 180, but then this is 90 degrees, right? Because that would essentially, that turns you the whole thing like that, which is correct. And then these 90 degrees kind of add to that column in here. So it basically what the other one, so what the other interference map would do is sort of the opposite, right? So it would tell you 90 degrees. So but at the end of the day, I mean, you should be like, the idea here would be, okay, so you would be able to apply. But this isn't okay. So, but this is applied. There's the Hadamards in between. This is when you're superposing. Because if you're not doing these, then nothing's happening. So you're here, right? First, you're superposing. First, you're superposing. But because it's a 1, this is already giving you the right combination. So this is actually not taking any action in here. It's not affecting anything. And this Hanomart, it's just gonna copy. So it's a partial superpose. Ooh, okay. Well, but technically, couldn't I just implement it like these, where I just do a full superpose? And then I say, couldn't I just do it like these? And then I say, so I start with this initial state, and this is my superposition. And then what I can do is I can basically say for the 1-1. So for everything that's got 1. So for this row in here, so it's got 1 in this qubit, right? Do a Z. No, because that only does. Okay, but that would be, yeah, but you could do it this way too. Yeah, okay. So this gives you these. And now I say, and now I say, because that's my point. Couldn't you just build the inverse QFT like these, and that's it? Isn't that? So now I wanna now I basically do the same, but with an S, right? Okay, no, that doesn't work. Of course not, because it's not what you want. What you want is you want it here. So for the no, sorry, you want for this column. So you want those to have 90 degrees. So you want the 0, 1. So you want these to be an S, and you want these to have an S. So you want it can be both. Yeah, here you go. Right? That's another way to implement it. But this is because I know. So this is when the actual input is not part of the circuit. Yeah, but that's actually makes sense, right? It doesn't have to be. The thing is, the QFT is implemented the way it is because we assume the starting point is the input. How useful is that? Because what this means literally is that I can say if I could. So if what happens if I put harmonics in between here? We'll just get back to. I don't know why I'm trying that. Why am I trying that? So the point is, because that's something that would then not be implemented with just this pair of, or these ideas of you've got, because this is literally a pattern of phasing, right? And the superpose basically is superposing. So for these, you would just define a way to interfere. Then you would say superpose, and then you kind of would say, so you would kind of have to come up with something else that's just phase, right? And so, and you do these with these. These could just literally be one interference map, or it's really a phase map, right? So you would just phase that, and that would give you So that would kind of give you but wait a second. Okay, but these, you would need to build that somewhat iteratively, knowing P. So here you would still need to, you actually would still need that for each I in P, kind of like the IMAP here would, it would just be this, right? Then you would kind of somehow build it in here. And then the result here at the end, right, you would kind of have. So what you want to have is you want to have these. Result here will look like. Well, and kind of you build that map iteratively, and then you just apply it once. So you just do it like that. And so you superpose a new face, and you're done. Yeah, maybe. So maybe this shouldn't be called interference, but just like wave, right? This is changing. So you superpose a wave, you interfere you superpose a wave that can cause interference, but you can also phase a wave. So you simply just phase a wave. And this is really, and this is really a phase map. Really a phase map. Yeah, I like the shape this is taking. Okay, so it's a wave, and then you can define a phase map, and then you can, but essentially what that would turn into is that would turn into a different circuit for each input. Okay, so, and the problem with that is that it would not be something you can just plug and play into another circuit. Because that's the advantage of, so building it this way, you would kind of rely on these functions generating a circuit for you. And this circuit will be different for every P, right? Because the way you would build that phase map will be different. So we'll call it phase map. Phase map, phase map, phase map. So I will have to update. That's still odd language. That's version. That's version 1. No, that's version 0.1. That's version the wave language. Version 0.1. That's yeah. It's version 0. Okay, 0.1. I'm bad at version numbers. I'm bad at everything, should be told. Okay, but let's focus on the. So this would be one way to do it, and that's kind of left to do here. So you would kind of you would build that based on P, right? So this is not like a standard. So you would superpose in phase. That's really what the QFT would do here. Now, so this is the inverse QFT, or I don't really know already what the inverse is, what the normal QFT is or is not. Now the trick is what's the other way around, right? So we have these. We have these here. Let's just clean it up. Clean circuit. So we have, what am I doing here? So we have these, and we want to turn it into a 1, and that's really the input that we have. Because the problem here is we can't have that input classically, because the bigger the register, the bigger this thing is, and that's the point of the quantum computer, okay? Because if you have 100 qubits, then we can't just represent that, right? So that's why maybe I need to rethink that as well, because this is not something you can, because I don't like that. I don't like that because that basically means you got to have the input separate. It cannot be in the circuit, and that's the point. That just kills the whole point of the quantum computation. Your state should be P. Okay, maybe let's try that then. So this is so still correct. It still gives me the output that I want, but it's not really. So this would be an inline implementation. Okay. So here, actually, our initial state would be P, right? So you would say, just initial state is P, right? So that's really the initial state. So there's no P in here. And now we can't just, let's think of how did these, did I lose that? So there was a swap in here. Then there was a Hadamard, and there was a Control Z, then there was a Hadamard, and then there was an S. Yeah. So, okay. So now we kind of have here partial superposing partially stuff, right? And we kind of, that's independent of that. So we're superposing starting from what about the swap? What do we do with the swap? Truth be told. Because qubit 1, the qubit 0 is the one that influenced the partial superposition. That's why you do a swap. Whereas here in Grover, it's really just phasing stuff. What you're doing. It's really just phasing stuff. Do we need something for swapping or we don't? I wouldn't like to have it. I'd like to have a way to superpose, to do a partial superpose. That would actually depend on the qubits somehow. A way to do that, right? The two operations combined. So to say partial superpose for this qubit, but with this value. That's complicated because that's the whole idea here. It's the whole idea. So we're how would we specify that in a way that it makes sense? I mean, you don't have to use the swaps in here, but then you're gonna have to swap at the end, won't you? Not either. What happens if I don't swap? So I have these. So if I don't swap, I gotta swap. I don't have to swap, but I then go to swap at the end. If I don't swap and I just stick to these like that, if I do a partial, and then I do like these, and then we do these, and we do these, then we kind of have to, you see the representation goes 0, 90, 180. Yeah. So then you actually have to swap in here, but you don't really have to if you know how to read that. Okay. Okay, but this is a way you can do it. Okay, so I'm just putting the problem for later, I guess. I'm just putting the swap at the end. Okay, so we're doing a partial superposition, and that kind of builds up. It just builds the pattern differently, right? But I guess the swap is something that it would just be a standard. It's sort of a matter of how you want to define your output, to be honest. What's the signature of your function, right? In this case, if we really want to have it sorted like these, where it just goes 0, 0, 0, 1, 1, 0, 1, 1 in terms of how the phases shift, then we really have to have the swap at the end. So I would need something like that, right? I would need, but then why not just swap things? But I don't know if that makes the whole building the whole thing more natural with this type of language. Because what I would say here is you now do a so you now do a superpose with the initial state, but it's not a superpose; it's a partial superpose. So you tell what qubits to superpose. So you specify, you say that's the seed, and then you say qubits, and kind of you give it a list of the qubits in here, right? Say qubits. Just give it 0, okay? So you kind of give it, let's imagine that we have the qubits somewhere in here. Like, let's imagine you have qubits, and then you kind of do this circ way. So you say circ line qubit, x for x in range 2. Okay, so we're kind of creating the qubits, and then we're saying, okay, so I want qubit 0 in here. That superposes you this way. Yeah, that superposes you. Then you kind of apply. Yeah, it's tricky. Maybe I'm looking at this from the wrong perspective. Partial superpose. Then you're doing. Why are you doing a control Z? This control Z, it's effectively useless in here. But you got to do it, right? The problem is the way that you easily interpret that is by saying that for the component where there is a 1, you still want to have a shift in here, right? Because if that would be this way, then it does make sense. Because then you got this 1, 1 in here. Feels a bit forced. It feels a bit difficult to abstract, to kind of go that level upper. Because the reasoning behind applying that operation, it really has to do with how your superposition looks like. Can I just learn how to switch tabs with my keyboard without just I'm just so okay. So you apply that, you would do because why would you? So what I would now do next is I would do an interference map, right? Or a phase map, as we call it here. Let's use version 0.2 of our language. That basically says for these states, apply a phase of 180 degrees. But why would I know this? Why would I know that this is what I want to do? I'm superposing on this qubit. And I'm saying that that makes absolutely no sense. It's not, that makes absolutely no sense. I'm just translating that because then what I would do next is so what's the sense of now? Okay, that's the phase map. That doesn't do anything to it. But now if I do superpose, if I do superpose, this is bad. So if I now do, I think I'm losing control on what are the parameters of these, but state equals circ wave suppose, and I would give it the phase map in the previous state, right? So, okay, so what's the interference here? Maybe we should take a look at these. What's the effect in here? Why would I know that this works well? Let's try to use some painting. That's getting a bit abstract in here. So that's my initial state, okay? So that's kind of what I have. I have 0, 0, so I have like a 0, 0, minus 0, 1, right? If I apply, if I superpose with a phase map, what I'm really doing here, is nothing. Why 1, 1? So that would be my question. As a programmer, why would I know that I need to apply, that I need to build such a phase map? Why would I know that I need to build a phase map this way? Phase map this way. 1, 1, 1, 1, 1, 1. Because what are the other phase maps that I would need to build? Like, if I have more qubits, okay, if I have more qubits, I'm always leaving one behind. Because here, nothing happens. So when you superpose, you already have what you want, don't you? Because then you're changing. Then you're just changing these two. Oh, that's complicated. That's complicated. Why would you know this? Because if you had a 1 in here, right? You want this, so it gets then superposed like that. So it kind of feels like the way, so the way this works, the pattern here is like you would first do, like, say if you have like if you have, I don't know, 3 qubits, right? You would do these, right? And these. And maybe 45 degrees, or I think so, right? Yeah, 45 degrees. So you would do something like that. Kind of, that would be. But why? Oh, that's so complicated. It feels totally unneeded. I'm trying to think from a programmer perspective, why would you know that this is what you need to do? It's like not all at once as a single phase map, but in combination of you would kind of. So what you would really need to do is these. Literally. This is what you would really need to do. But why would you know that that's what you need to do to build these? Right? Because that's not even what you're building. Um, and of course, your initial state being not even that. So the qubits. This should even be like these, like these, and like that. So that code, if that would exist, that would be the code, and then you still need to swap. You would still need to swap things. So you still need to swap these two qubits for you to get the actual output as you wanted to have. But how would you know these? How would you know these? How would you know these? Let's think. Let's think, okay? We're here to think. We are here to think. I love this one. It's just 2 lines of code. But it doesn't make any sense because it generates a different circuit every time, and we don't want that because we want those circuits to be pluggable into other circuits. And so we want the actual wires to carry the input. And here, of course, this will be the state, right? So, and we're doing 3 qubits, right? So that would be really that would be really the thing, and you would still need to swap somehow. 0 Q2. Let's think about this. What it means to phase 111, and what it means to superpose with these. Okay, I don't know. Because if you think about a superpose where you just have an initial state, that's the seed. Isn't this literally like, actually that's like you give it an empty phase map, right? Yeah. So all what this is doing is basically, yeah, it's doing a superposition in combination of phase shifts, which is really all what you need for it's all what you need for interference, right? Curious how we can add entanglement to these later on. But okay, let's think about these. So this is another way to implement the QFT for 3 qubits, where the initial state is the input. Why would these make sense? It's pretty nice, to be honest. It's pretty elegant, right? So the reason you need to do it this way is because what? I feel I'm asking the question, expecting someone to answer, actually. That's not going to happen. So what happens when you do, let's take a look at this again. So what happens when you do can I clean that up? Stop this. Yeah. So when you have a 111, right? Well, at the end of the day, that's actually pretty similar to these, right? Really, actually, that's pretty similar. So you're balancing towards these, regardless. Oh, wait a second. Regardless regardless of the seed of your superposition, which in this case is the initial state, is the actual input, right? So you're literally, you're creating a superposition that's seeded by 0, 0, 1. Step by step. So you're superposing only a qubit. What does this mean, right? Exactly. So maybe it's got to do with this qubit and this qubit. They're both ones. Because if I superpose these, right, I'm ending up with, so let's do the case. Let's do the case, okay? So this would be, and that would be a T, correct? And I would miss a Hadamard in here, and I would miss thing here. What? No, what am I doing? Hadamard Z. Oh no, that's the way you do it. Really? Yeah, that's the way you do it. Okay. Oh no, that doesn't look good. That doesn't look good at all. What? What did I have before that? With 2 qubits. Yeah, I had these, right? So, oh no, okay. So I had these. So now I'm just adding one more. That stays the same. But this is now still controlled by this, isn't it? Or not? And then a Hadamard in here. And a T in here. It's the other way around. So these would be, no. Am I not missing an S in here? I forgot how to do that. QFT for 3 qubits. Awesome. Like this. Am I right? No. What's wrong? What's wrong with these? What's wrong with these? I'm not so sure if this is the correct thing then. That's not how this looks like, or is supposed to look like, right? It's damn complicated. That doesn't affect, because we have a 1, right? So we want this to be like, just gives a full circle. Then we do these, and we control on an air, on we control and we do an S. T. Why not a, so it does, so you have these, and now I would need, but what I would need in between here is, so that's fine, but I'm missing 90 degrees in 0, 1, 0. Have I just, I'm getting dizzy. Um, because then this literally means that's not correct. That is not correct. So QFT, inverse QFT. All my videos. That's nice. Without the swaps, that's also something that I answered. Oh man, it's all about my. That kind of sucks, to be honest. So here we have. What's this? Like that. So you're doing. So the rotations are. Okay, so here indeed there is supposed to be an S rotation and then a T. Is that correct? Yeah, and then S rotation and a T. And then a T. Is that correct? Almost. Oh, I'm missing a Haramart at the end. Wait a second. Oh, no, there's no T at the end. What am I doing? No, there should be. What am I doing here? Can I just put these side by side? So, where am I now? I lost it. I lost it here. So start with the Haramart, then oh, that T is not needed. That T is not needed. So a Hadamard, then you have the S, and you have a Hadamard. That should be it. I don't know. What have I messed up? Um, mm, 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 mm. So what if I just clear all and open them in here and take a look at quantum Fourier transform? Okay, but this one has the actual swaps in here. Okay, yeah, so it's doing these. Wow. So if I would put the swaps at the end, I would have to do it all the other way around, right? So if I would just say, get rid of these, get rid of all these, and just keep 3 qubits, just keep the 3 qubits. So you would just have these swaps in here, and kind of like, can I just get rid of these things? And so out of this. And if I want to have the swaps at the end, my guess is I have to because I want to have the one in here, right? So that takes me to. No, something's wrong in here. I start off with 0 degrees, then I go to these, I go to these, then I go to these. Yeah, that's all not needed. That's the now that's the point. Here we go. Okay, so if I wanna have the swaps at the end, I have to basically um, don't like that. Why is it that I don't like that? Why is it that I thought I could have the swaps at the end? And it was working for 2 qubits. If I would start with there's no Z in here. I cannot have this. I want to have the swaps at the end. So I just literally need to, if I want to have the swaps at the end, I literally need to move things around, right? That's the only option that I have. Yeah, that's all overcomplicated. I think I need to think about these. I need to think about these. It's not really comfortable with these, but it's not so. It doesn't seem impossible, but it's definitely complicated. What the hell is this? Okay. I just want to make sure that these kind of has a meaning, right? That it has some sort of meaning. And so maybe the swap needs to be at the beginning. It's easier this way. I'm sure there's a way to rearrange those operations so the swap it can be put at the end. But the swap, I'm not going to get rid of the swap. That's the thing. I'm not going to get rid of the swap. And so, but the swap is something that it implicitly has to do with the fact that the interpretation is this number one here basically tells you how do you need to rotate here, right? So if I want to swap at the end, maybe I should start like these first, and then yeah. I should kind of mirror it. Yeah, of course I could mirror it, right? So would that work if I say that you start with these, then you do these, then you do these, yeah, and then you do these. Okay, here you go. Yeah, here you go. Here it is. Yeah, I like that. Okay, but I'll leave it here. So this was so this is this. I figured it out. Spent probably 20 minutes on this, but okay, because I feel more comfortable having these at the end, because this feels a bit more like it's just a formatting issue, right? Whereas the trick here is how do we apply those partial superpositions and those phase maps. And so okay, so this kind of, it's the other way around. So it seems like it seems like uh, you could kind of would start this way. And so you would say here you actually have, and here you have, yeah, that's an interesting map, right? Because that's a combination of two different rotations in here, to be honest. So that's not, it's not 180 degrees. Combination of two phase patterns or phase shifts. Go here somehow. Then you've got one in here. That's definitely, and then actually there's none. Okay. No phase shift needed. Shit. Shift. Anyway, I'll just go ahead. I don't want to make this video too long, and I just yeah. All good. All good. Perfect.